This video demonstrates how to use CANDO and JupyterLab for calculating relative binding free energies for a set of molecules sketched in the Calculate Cheminformatics library widget. This demo can be found in the CANDO Demos GitHub repository as 06 Demo Sketch Thermodynamic Integration from the link in this video's description. To begin using this demonstration notebook, choose Run from the JupyterLab menu bar and then choose Run All Cells. This will initialize all the widgets contained within this notebook. This demonstration provides a preloaded workspace called Demo 06. In step 1, choose Open to load the respective data into the notebook. The Messages window will notify you when the task is complete. As you can see, Step 2, Load Receptor, and Step 3, Load a Template Ligand, have been populated for you. In this case, the receptor is thrombin S1, and the ligand is D-phenylalanine, N-benzyl, L-prolenamide, abbreviated in this notebook as DIPHE. In Step 4, we see the Calculate Sketching widget. The Calculate Sketcher has all the controls for creating any type of molecules for doing structure-based drug design. This demonstration contains several pre-drawn DIPHE ligands. Each ligand has a modifying pyridine ring, showing how this tool can be used for drug discovery methods such as positional analog scanning. We can also see the addition of several substituents, which will be combinationally added to the corresponding molecules using the numbered asterisks. Once you're satisfied with your sketch, click on the Parse Ligands accordion to create your set of molecules to be used in the TI calculation. The View Ligands accordion will automatically open, showing on the left the 2D sketches of your ligand in a drop-down list, controllable via the slider. On the right, an NGL view window contains 3 items: the receptor, a template ligand, and the chosen ligand from the drop-down list on the left. All of whose representations can be controlled using the selection boxes. In addition, the user may also modulate a clicked dihedral angle of a selected ligand using the slider on the far right. This feature is not required for this demonstration. The chosen ligand has been fit to the template during the prior Parse Ligands calculation. As you can see, there are instances where fitting is not quite optimal. In this case, the user may choose to jostle button to randomize the coordinates of the chosen ligand and perform an energy minimization, which typically leads to an optimal template overlap. It is not required, but it is good measure to check the overlap of each molecule before proceeding to the next step. Future versions of TI Run Sketch will include improved molecular overlapping and docking features. In Step 5, the user may down-select the ligands to be included in the TI calculation. All ligands are selected by default. Click the blue checkbox to remove a ligand from the calculation. Alternatively, Select All or Select None buttons may be used correspondingly. In Step 6, we'll be creating an optimal calculation graph for the chosen set of molecules to be included in TI calculations. This algorithm is roughly based on the low-map formulation. When the calculation is complete, a cytoscape graph of molecules connected by edges is presented with associated similarity scores. The drop-down box allows the user to display the graph in several different formats for viewing the results. By clicking on an edge, atoms for which a soft core potential will be applied during the TI calculation are highlighted in yellow. Molecules with very high similarity score due to single atom substitutions will be treated as identical in the graph, although these atoms will be included in the TI transformation parameter files. There are instances, as we see here, Where overlaps between molecules or between the template molecule and a chosen molecule persist. This is apparent by the calculation graph indicating that a large portion of unambiguous similarity be included in the softcore region. These cases are simply resolved by noting the affected molecule's name and returning to the View Ligands widget of Step 4. On the left, in the ligand dropdown, select the affected ligand name. On the right, click Jostle to randomize and minimize the affected ligand to the template ligand once again. Return to Step 6 and click off the graph. Clicking the affected edge once again, we see the issue has been resolved. Step 7 allows us to configure the simulation settings that will be provided to AmberMD. Optimal settings for water box size, simulation times, step size, and softcore potential constraints have been provided, although the user is free to adjust these parameters in any way they choose. Configuring the calculation is done by providing a directory name and choosing either 3-step, decharge van der Waals recharge, or 1-step TI calculation setup. If a directory of this name already exists, the message window will prompt for a new name as to not overwrite any existing data. In the next accordion, click Start Task. We'll write out all AmberMD and CANDO files required to perform and analyze the TI calculation. This is written to the jobs directory of the user's home folder. A tar file is included for easy transfer to clusters and cloud computing resources. Please visit our YouTube channel for other demonstrations of the CANDO JupyterLab environment. If you enjoyed this video, please subscribe and leave a comment to see more videos like this one. If you would like to use CANDO and would like help getting started, please leave a comment or contact us via our webpage at thirdlaw.tech or one of our social media accounts linked in this video's description.